Check it out now, y'all.
nanoHUB-U, online instruction.
Hi everybody, welcome to nanoHUB-U. This is the third week of lectures, and it's going to be focused on finite difference time domain. In particular, we're going to discuss the main concept behind finite difference time domain, and particularly why we would like to even consider implementing this approach for solving partial differential equations, which are coming from Maxwell's equations, and then basically some of the nuances of how they're implemented, and then ultimately we'll look at some specific uses and examples to kind of give us a feel for what can be done with this sort of strategy. Okay, so without further ado, here's the equation for light propagation that we're mainly going to consider with finite difference time domain. Okay, so these are effectively Maxwell's equations here. But you'll notice a couple things. First of all, you have basically Faraday's law, but then it has two extra terms, okay? And there's this so-called fictitious magnetic current here, and then there's also fictitious magnetic conductivity. And so without saying too much about it right now, we're just going to say that in regions that are not places where fields are actually being measured and compared to experiment, this may be useful, for example, to increase absorption and to prevent back reflections in small propagation domains. And then here you can see that we actually have Ampere's law with Maxwell's correction. That's the dd by dt term. And then this J will be basically the source of our fields in the system, and then the sigma d times d will basically be the source of material absorption. In this case, we're looking at an ohmic loss. And then you also notice that there are these kind of standard auxiliary equations that relate the d field, the displacement field, to the electric field E via a dielectric function epsilon. And then there's also magnetic permeability function that relates the H field to the magnetic field B by a factor of 1 over mu. So how are we going to implement finite difference time domain on Maxwell's equations? Basically, we're going to take those equations I showed you earlier and then implement them on what's called a Yee lattice or a Yee grid. And the kind of the basic concept of the Yee lattice is shown here. And so basically you have all space is discretized in 1D, 2D, or 3D, and also the E fields and H fields are actually staggered in their positions relative to one another. And so that might seem a little odd, actually, like why would we even think about doing that? And so hopefully, like by the end of this lecture, you'll get a better idea of why. But effectively, what we want to do is to alternate evaluating both Ampere's law with Maxwell's correction, and then Faraday's law. So we're going to basically time step the E fields and then the H fields. And then if we do everything properly using the so-called leapfrog method, then this should give us lower errors than a more naive approach. And so this would converge as 1 over the discretization squared. And so that would tell us that as we make the lattice smaller and smaller and also have slower time steps, then eventually the accuracy will converge very rapidly. So that means that we won't need arbitrary number of computer resources in order to accurately simulate results, and we can see nice convergence. And one example of a tool that's implemented this technique is called MEEP, but certainly MEEP is not the only tool that's out there to do this sort of thing. So now let me try to explain like what is the general premise behind solving differential equations. And so if we have any equation that's basically a time derivative set equal to some function of that same variable, so dx by dt equals f of x, then we'd like to solve it as accurately as possible, but without using too much in the way of computational resources. So there are two classes of problems where we're trying to solve this sort of equation. The first is a so-called initial value problem, where we know what the values are, maybe at time t equals 0 or some other start time. And then the other is actually boundary value problem, where oftentimes we'd be trying to solve for what happens like between two domains. So if you're trying to solve Laplace's equation, that would be a good example, boundary value problem. There are many algorithms to solve differential equations, and I won't go through everything, but one approach that's well known is called the Euler method, and I'll explain that in a minute. Then there's also higher order methods, which refine on the Euler methods, shooting methods, which are simple but risk a lot of instability, and then finally finite element and finite difference methods, which will be kind of our concern. Okay, so how does the Euler method work? I think conceptually it's very simple. So you had this dx by dt, and so now you just move dt to the right-hand side, multiply both sides by dt, and then you discretize time. Okay, so now we have something like dx is equal to d delta t times f of x. Okay, so I think conceptually it's very simple to think about. Now, there's a big problem, which of course is that if delta t is too large, then your updates to delta x are not going to really reflect what should be happening in the system. So of course, the problem is that you're implicitly assuming that there's linear evolution of your x value. And so then x just goes linearly with time. Now, some differential equations, that would be exactly true. Obviously, those ones you can probably solve analytically. In most problems where computers are needed, of course, it won't necessarily just be purely linear. And this could fail badly, especially if the ODE had a lot of curvature. Okay. But of course, in most cases, we can pick a small enough step size so that it does become linear. The only question is how much in the way of resources do we need to use? So another approach is, rather than just like kind of assume that we have to get it down to the point where it's highly linear regime, we're actually going to incorporate like more than one derivative into the solution. And so we'll look at both the first derivative and maybe the second derivative. So then if we can incorporate up to the nth derivative, then we could reduce the errors down to 1 over delta t to the n plus 1th order. Okay, so even with the first derivative, we should be able to get down to 1 over delta t squared. Obviously, the Euler method's not giving us that right now. But there is another approach called the leapfrog method that might help. And so here, I kind of explain the concept. So here, basically, you're looking at both the position and velocity of some particle, okay? And then, of course, you know that the derivative in time of the position is just velocity itself. And so you get dx by dt equals v. And then for dv by dt, that's basically a measure of the change in momentum divided by mass, and so then this becomes f over m. Okay, I just wrote it as f, assuming m equals 1. And so now we have this set up. So this allows us to basically evaluate Newton's law in a more accurate fashion if we basically alternate updating the position and the velocity of our particle. And so you can see here, basically, I have a second order expansion, a Taylor expansion of x in terms of vi times delta t plus this second order f times delta t squared. And then you also have a first order expansion of vi, which is dependent on fx and fxi plus 1. Okay, and so then the key thing that's being achieved here is that you're taking the average force over the time interval over which this calculation is evaluated. And then this is allowing you to account accurately for acceleration, especially if the force itself is not varying very quickly, and still accurately track the fact that the system is accelerating. And so therefore you get like kind of a quadratic speed up in the position over time. So hopefully that's very intuitive. Now, there are, of course, other methods that are more complicated. One example is the Runge-Kutta method that incorporates spacing for points that are separated by less than delta t. And so one example of this implementation, basically you define a set of k sub i's. Okay, and then the idea is that you'll construct k sub I basically by choosing these like kind of fixed intervals in both time and like the dependent variable y at the same time. And it's basically written in this form where you have ki would depend on this delta t times this function evaluated at very special times and positions. And then basically this is set up so that every time you solve for a ki, then you can start to incorporate all those ki's into the next step for y. And so then this allows you to kind of continuously update the y variable, incorporating higher order terms. And so this is, in some sense, like a more general approach than what I showed earlier. And therefore, the accuracy should kind of scale in the same way that I said was theoretically possible, 1 over delta t to the m plus 1, if we have m k sub i's. Okay. So if we compare this to the Euler method, then this is obviously not a huge change when m equals 1, but it is more accurate. But then as we go to higher m's, of course, it gets more and more accurate. I think the ODE 4.5 tool in MATLAB, that should be accurate to the 5th order in delta t. Now, there are also some special solvers that can account for very rapidly oscillating problems. And so then this uses what's called a backwards differentiation formula. And so here you can see that basically you would write a sum of y's in this form, and it would basically be able to kind of, I guess, look back at kind of your later solution in order to update that correctly. And so if this is implemented properly, then this can actually increase your convergence by orders of magnitude. This is implemented in MATLAB as well as ODE 1.5s. And so this allows you to get like high order accuracy. And there is something else called like a rotating wave or envelope type approximation in which you would analytically convert a rapidly oscillating problem to a slowly oscillating one. And so then that's another trick that can be used. Now, of course, since I was talking mainly about ordinary differential equations, we have to make the transition to partial differential equations. And the key independent variables now are going to be both time and space in electromagnetism. And the way that we can approach this is we can start with like all the ODE methods that we just discussed, including the leapfrog method, but then we need each of those solutions in time to also talk to its neighbors. So that's really the key point. And the fact that causality is respected in electromagnetism means we never need to talk to every single neighbor at every time step, because that would be catastrophic for the time of evaluation. But instead, on each time step, we can just talk to the nearest neighbors. So now what we're going to do is basically take the electromagnetic equations, and then we're going to put them on what we call a Yee lattice, like we mentioned before. And then we're going to make sure that the neighbors talk to each other based on Maxwell's equations. And we're going to basically use an ODE-like approach to step through time, alternating both the electric field evaluation and the magnetic field evaluation. So if we write Maxwell's equations down in 1D, then we can actually write them in a much nicer form than we had earlier. So in the simplest case, then effectively we get something that has a time derivative in terms of h and a spatial derivative in terms of e. And so this is essentially Faraday's law. Okay, dB by dt equals d curl of e. Okay. And then the second equation is Ampere's law with Maxwell's correction, but we've dropped the current for now. And so we basically end up with capital D by dt equals the partial derivative of h with respect to space, or curl of h. Okay, so it's actually a very simple set of equations, and now we just have to discretize them on a 1D chain at a given time. Okay, and then we have to start these neighbors talking to one another. So if you look at this chart up here, what you can see effectively is that we have E fields at different positions, okay, in space, and that's in the x-axis. And now we've illustrated time on the y-axis, okay? And so what we're doing is we're discretizing both in space and time, okay? So in order to get the partial of h with respect to t, then we basically take the difference of the h fields at two neighboring positions, and then we divide by delta t. So this would be kind of a central differencing method. And then for the spatial derivative of E, then we basically are looking at basically the difference in this direction. Okay, so the key point is we go in this direction for time derivatives, and then we go in this direction along the x-axis for the spatial derivatives. And then when we combine those together, then we end up with an equation that looks like this, where basically you see that the difference between the two h fields is related to the time index, which is listed here as q plus 1 and then q minus 1/2. Okay, and then in this other one, we have difference in spatial indices. So m and m plus 1 are basically two different spatial derivatives, or positions, sorry, which are illustrated here and here. Okay, so hopefully that makes sense. And then we ultimately get two update equations from that sort of write-up. And so the first equation is coming from basically rewriting the equation I just showed you, so that it's basically in the new h field in terms of the old h field plus all the changes. And so that's done by basically multiplying by delta t over mu, and then adding h of q minus 1/2. And so then we end up with this equation here. And then the second equation here is constructed in a very similar fashion from the other Maxwell equation. And so we end up with, again, another equation where the new E field is the old E field plus this delta t by delta x over epsilon times the difference of h's. And then if we alternate solutions at t plus 1/2, and then t plus 1, t plus 3/2, t plus 2, etc., then we can get second order accuracy using what's essentially a leapfrog technique. However, there's a key question remaining, which is what do we do in higher dimensions? And so then this is where the Yee lattice is very important. And you'll notice that the Yee lattice is basically staggering the E and H field locations by half a grid point. And based on the explanation from earlier, hopefully it makes sense that you would have the E fields on the edges and then the H fields on the face, because basically you're trying to update E fields by collecting H fields from the neighbors. Okay, so then when you average them out using central difference approach, then they end up at the same location as the E field that you're trying to update, and then vice versa. And so then that's why you get the maximum numerical accuracy and efficiency as proposed by Yee in 1966. So in the next lecture, we'll discuss 3D FDTD in more detail, and would recommend you start looking at the MEP reference manual to understand more.